Hey guys, welcome to my YouTube channel Stats1304. So this video is going to be in continuation with my previous series, Fundamentals with Mathematical Statistics. So my frequency of uploading videos on this playlist will be one video in every 2 weeks. I know my frequency has been lower here and I haven't been that consistent. The reason for this is I wanted to complete some portion of multivariable optimization, my other series which is going on. So also check that out if you haven't seen any videos from multivariable optimization. I want to complete some portion of multivariable optimization before moving on to statistics. Right, so this video is going to be a proof on why correlation lies between -1 and 1, and the next video that I'm going to record on this playlist, which is mathematical statistics, will be on random variables and trying to find the covariance and correlation of discrete and continuous random variable, right? So please bear with me and keep liking my videos, sharing my videos and subscribing the channel. Yeah, so let's start now. The question in front of us in this video is why does correlation lie between -1 and 1? Why does the correlation coefficient lie between -1 and 1? So I'm going to show you a proof. This proof is not very tough to grasp. So once you learn this proof, you will have a intuitive understanding of why correlation lies between -1 and 1, right? So first let me write some terms so that you guys understand what is correlation. So correlation can be represented by R also and by this symbol also. So I don't exactly know the name of the symbol. If anyone knows the name of the symbol, please do write it in comments. I guess it is rho, right? So the formula for correlation is covariance x comma y divided by standard deviation of x and standard deviation of y, right? Or I can write this also as covariance x comma y and the root of the standard deviation of x and the root of variance of x and the root of variance of y, which is the same thing essentially, because this is variance and the root of variance is sigma x, which is standard deviation of x, right? In a similar way, sigma square y is the variance of x and this is the variance of y. This is the standard deviation of y. Now the formulas for covariance of x comma y is sigma xi minus x bar into yi minus y bar divided by n. So this is my formula for covariance of x comma y, and the formula for the variance of x is sigma n x minus x bar whole square. So if I want to find out the root of this, which is the standard deviation, it will be the root of sigma by n xi minus x bar whole square, right? So I'm writing this formula in terms of deviations and not expectations. So there is also an alternative formula for writing all of this, which is in terms of expectations, but now this proof which I'll be solving right now will deal with deviations and not with expectations. So I'm not using the expectations notation here, right? So I've explained what is covariance, what is standard deviation, what is variance, what is standard deviation, and if I write for y, it will be variance of y is sigma by n yi minus y bar whole square, and the standard deviation of y will be the root of this. Right, so what is the formula for correlation? What is the formula for correlation? So the formula, this is correlation between x comma y which is this, and this is covariance. This is covariance. Covariance. COV. Covariance. And can also be written as, now this formula of correlation can also be written as correlation x comma y is equal to the covariance. So what was the formula for covariance? This was my formula for covariance, and this is my formula for standard deviations, right? So I can write this formula as, if I just keep my denominator same, if I just write my denominator as sigma x only and sigma y only, now I'm only changing the numerator. Numerator is covariance of x comma y. So my covariance of x comma y will be sigma by n x minus x bar into y minus y bar. Y minus, so this is my correlation. So x minus x bar and, wait a minute. So this is sigma y, sigma x, standard deviation of x and standard deviation of y, and sigma by n x minus x bar into y minus y bar, right? So this is my correlation. Now let us start the proof. Let me just copy all of this so that you guys can keep a track of what is happening. So let me just start my proof here. So we have to remember these three formulas, right? We have to remember these formulas. So this is the first formula that you should keep in mind. The second formula, this is correlation. So covariance of x comma y is this is my covariance. So keep this formula in mind, right? And also remember that my sigma x is equal to sigma by n x minus x bar whole square. Sigma y is sigma by n y minus y bar whole square. Now let me start with the proof. So keep these four formulas in mind. 3 and this is 4. So these four formulas we have to keep in our minds, right? Oh, this is better. This is much better. We have to keep these four formulas in mind. So 121 should be the perfect magnification. So let us start with the proof. So proof correlation x comma y lies between -1 and 1, right? So for proving this, what I'll be doing, I'll be writing this term x minus x bar divided by sigma x plus y minus y bar divided by sigma y, and the whole square of this is greater than equal to 0. Now you will be surprised and you will start thinking, what is this guy doing? So if you notice this, anything, if you square anything, that term will always be greater than or equal to 0. So if for example I have -3, and if I find the whole square of this, I'll be getting 9, and 9 is always greater than equal to 0. If I try to square -half, I'll be getting 1/4, which is always greater than equal to 0. If I'll be squaring 0, I'll always get something greater than or equal to 0, which is 0 only. So 0 is equal to 0, hence 0 is greater than equal to 0, right? So every time you square something, you always get something which is greater than or equal to 0. So based on this fact, I'll be using this term and showing you why correlation lies between -1 and 1. So now the proof starts. So I'll be just squaring this whole term. So we'll just try to find the square of this whole term and keep the sigma term outside, the sum term outside, I'll be getting x minus x bar whole square, sigma x whole square, and I'll be sigma x whole square, which becomes sigma square x. So the square of my standard deviation becomes variance. So sigma x whole square, right? And y minus y bar whole square. So this I'm just applying the identity of a square plus b square. A plus b whole square is a square plus b square plus 2ab. So now I'll be getting a 2ab term, which is 2 into x minus x bar into y minus y bar divided by sigma x sigma y, which is greater than or equal to 0. So this whole term is greater than or equal to 0, right? And I also have the sigma term here. I also have the sigma term here, right? So now I'll be just solving this. So if I divide the whole term, if I divide the LHS and the RHS both by n, so first of all what I'll be doing is I'll be giving the sigma term x minus x bar whole square sigma x whole square plus sigma y minus y bar whole square divided by sigma y square plus 2 times, now sigma goes inside, x minus x bar into y minus y bar divided by sigma x sigma y. This is greater than or equal to 0. This whole term is greater than or equal to 0, right? So now if I divide the both the LHS and the RHS by n, I'll be getting the same term only, right? If I divide the LHS and the RHS by n, there won't be any difference, right? So I can do that. So I'll be using n to reach to my required goal. So if I just divide this by n, and if I just divide this by n, two times sigma by n this is greater than or equal to 0. So now what I can do, I'll be just writing this in a way that you guys can relate to this. So I'll be just sending this n inside, x minus x bar whole square plus sigma square y, sigma by n, y minus y bar whole square plus now 1 upon sigma x into sigma y. Wait a minute. Two times 1, and this is sigma by, or I can write this as the same thing. I can write this as, give me a minute. So I can write this as sigma x sigma y and sigma by n x minus x bar into y minus y bar, and this should be greater than or equal to 0, right? Now let me zoom out. So what is this term? Sigma by n x minus x bar whole square. What is this term? This term is the variance of x. What is this second term? This second term is this term, only this term. This term is sigma y minus y bar whole square. So this term is this variance of y. And what is this term? What is this term? What is this term? What is this term? This whole term. What is this whole term? This whole term is correlation, right? This whole term is correlation, right? Because the numerator becomes covariance and I have standard deviation of x and standard deviation of y in my denominator, so I have correlation of x comma y. So now let me just return and solve this. So what I have is this. So I'll be representing my correlation x comma y. I'll be representing this by r of x comma y, or I'll be simply writing r. So my proof becomes, my r lies between -1 and 1, right? So this is the first part of my proof. So now I can write this as, this becomes 1 by, so this becomes 1 upon standard deviation of x, 1 upon variance of x multiplied with the variance of x again, because this is the variance of x, and 1 upon variance of y multiplied with the variance of y, and plus 2 times r, because this is my correlation. This whole term is my correlation, right? Now let me remove the box, right? So this should be greater than equal to 0. So if I just cancel this out, this term and this term gets cancelled, this and this gets cancelled, I'll be left with 1 plus 2 times r, which is this term. I'll be left with 1 plus 2r greater than equal to 0. So I have 2 plus 2r greater than equal to 0, which gives me 1 plus r greater than equal to 0, which implies r is greater than equal to -1. R is greater than equal to -1. R is greater than equal to -1, right? So we have proven that r should always be greater than equal to -1. Now the second part of my proof. For the second part of my proof, I'll be using the a minus b whole square identity. So earlier I used a plus b whole square identity, which was this term, a plus b whole square identity. Now I'll be using a minus b whole square identity. So let me just duplicate this once. So now I know that my correlation coefficient, which is r, is greater than equal to -1. So I'll be using a minus b whole square identity, right? So I'll be replacing this plus sign with the minus sign, and I'll be using the second part. Let me just check once. This is my first part and this is my second part. So my a minus b whole square identity. So if I just use this identity, I'll be getting sigma x minus x whole bar by sigma x whole square plus y minus y bar whole square by sigma y square plus minus, so a minus b whole square, so minus 2 times x minus x bar into y minus y bar divided by sigma x sigma y. This should be greater than equal to 0, right? So now I'll be separating and dividing by n at the same time. So I'll be just taking this out, sigma square x, and I because this variance is a constant term, right? Variance is a constant term, it is a number, so I don't need to include this in the sigma term here, right? For now. But in correlation coefficient, in correlation coefficient I need to include this standard deviation because it comes as a part of the formula. That is why I included in the sigma sign. Actually, if you see, it is also not included in the sigma sign. It comes in the denominator, right? And sigma is basically in the correlation coefficient. I'll be showing you that sigma basically deals in the numerator only, right? So I have x minus x bar whole square, and sigma by n 1 upon sigma y square. We erase this, plus 1 upon sigma y square sigma by n y minus y bar whole square minus 2 times sigma by n, and if I just take the n to the numerator and divide, so I can write this as sigma n x minus x bar y minus y bar divided by sigma x sigma y, and this should be greater than equal to 0. Now you can see that sigma is only part of the numerator here only, here also, right? Though it can be included in the denominator also, there is a different form for that, for representing correlation coefficient. So I can write correlation coefficient, which is r only, rx comma y, which is the correlation. I can write this also as sigma by n x minus x bar y minus y bar in the term of deviations, and I can represent this by sigma by n x minus x bar whole square and sigma by n y minus y bar whole square, right? So there are different ways and different forms, but right now I am not using this form. I am using this form only for the numerator, so that my proof becomes easier. Now what I'll be doing, this becomes my sigma x square, which is my variance of x. This term again becomes my sigma square y, and this term becomes my correlation coefficient, correlation of x comma y, which is r, right? Now I'll be just completing my proof. This whole term becomes r, right? So now this and this gets cancelled, this and this gets cancelled. I have 1 plus 1 minus 2r greater than equal to 0, which implies 2 minus 2r greater than equal to 0, which implies 1 minus r greater than equal to 0, which implies 1 is less than equal to, sorry, r is less than equal to 1, which implies r is less than equal to 1. So this will be my second, and this was my first. So from 1 and 2, therefore from 1 and 2 I can say that, so 1 was r is greater than equal to minus 1. This was my 1. And r is less than equal to 1 was my 2. So this was my 1 and this was my 2. From 1 and 2 I can say that the correlation coefficient always lies between minus 1 and 1, where r is equal to the correlation coefficient between x and y. So I'll be ending the video here only, and I'll be sharing the PDF of this file in the description, so please check that out. And if you have any doubts, if you want me to clarify anything, again I'll be happy to do that. Please like the video, share the video, and again I'm not so consistent with my statistics playlist, because I again want to focus more on the multivariable optimization aspect, and that playlist first I want to complete some portion of, and then I'll be moving here. But in the meantime I'll be trying to bring up more content, and the content that I'll be bringing up will be mostly focused on random variables and joint contrast distributions. Also my pattern of uploading videos on this playlist will be a video every 2 weeks, right? So I hope you keep watching my content, and please keep subscribing the channel. I know that I'm not so consistent on this playlist, but once I have completed some portion in multivariable optimization, I'll surely come to this playlist and start uploading more videos. In the meantime, just watch it, share it, and please put in a comment, even if you're angry at me, even if you want me to upload more videos. I'll be motivating myself more, but please put in a comment and like the video, share the video, and subscribe the channel, so that I am encouraged to put in more videos. Also, if you are a person who only watches statistics and is only interested in statistics, I would urge you to please watch multivariable optimization also once, because it is also a branch of mathematics only, and I am too excited to teach it. So please watch that, and thank you for watching this video. If you have made this far, thank you so much. Bye bye, and I'll see you in the next video. The next video is also coming up soon. It will be on covariance and random variables, so using discrete and continuous methods to find the covariance and correlation, right? So thank you so much, and bye bye.